Shri Gurubhyo Namaha, children. Today we are going to start with the second chapter, electrostatic potential and capacitance. Now, the first chapter we were learning about static charges, and we started with Coulomb's law, followed by electric field due to a point charge. Then we learnt about electric dipole, then electric flux, and finally Gauss law. So all these we were learning with respect to a concept called electric field, which is considered to be a vector quantity. Now here in this chapter, we are going to talk about electrostatic potential, which is also the characteristic of a charge, but here electrostatic potential is considered to be a scalar quantity. Okay, so let us move on to this topic, but before we move on to that, I wanted you to recall about conservative forces, what you learnt in 11th standard, and also about potential energy. So let us refresh it and then start with our topic. So what is a conservative force? Now when you move a body from one point to another, let us take two positions A and B. Assume that a charge is there or a body is there at B. Now I wanted to shift this body which is at B to A. So what should I do? I should do some work, and that work should be done by an external force. Okay. So work done by the external force in moving the body from one point to another. Now that work is stored in the body as potential energy. We define potential energy to be the energy stored in a body, which is called as potential energy. Now when you remove the external force, the body once again starts moving. Now whatever potential energy has been stored in the body is converted into kinetic energy, and thus the total energy, which is the sum of potential energy and kinetic energy of the body, is conserved. So this is called as conservative forces. Now here what is happening when you move the body from one point to another? The work what you are doing is independent of the path. That is, the work you do does not depend on one path. For example, let me tell you, now this is point B, this is point A. Now I am going to shift a body from B to A. I can do like this, or I can do like this, or I can do like this. Anyway, I can shift the path. The path that is traveled by from B to A, it may be anything. Okay, so the work done in making the particle to shift from one point to another does not depend on the path. So these type of forces are nothing but you call it as conservative force. So examples of conservative forces are spring force and gravitational force. Now you would have read about gravitational force in 11th standard. Now here is the gravitational law. F is equal to minus g into m1 m2 by r square into unit vector. Now here I have written Coulomb's force. F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Like how gravitational force is said to be a conservative force, now Coulomb force between two stationary charges is also a conservative force. Now both these laws have inverse square dependence. That is, the force is inversely proportional to the square of the distance between. Here also the Coulomb force between any two charges, it is inversely proportional to the square of the distance between the charges. So whether it is gravitational law or Coulomb law, both have the similar property of inverse square dependence, and their proportionality constants are replaced. One now gravitational force has a proportionality constant G. Now here Coulomb force has a proportionality constant K, which is equal to 1 by 4 pi epsilon naught, and the masses in the gravitational force are replaced by the charges in the Coulomb force. So gravitational force and Coulomb force, so gravitational force and Coulomb force, they are said to be conservative forces. Clear? Now, when you consider a system of charges, the charges of the system exert electric forces on each other. System of charges, in the sense you have a system which consists of a number of charges. Now all the charges will exert electric force on each other, definitely. Okay, if charges are existing in a system, definitely there is an electric force that is existing between them. Okay, now if in this system of charges, if you change the position of one or more charges, now to change the position, you need to do some work, and that work is done by the electric force, right? So we define change in electrostatic potential energy of the system is the negative of the work done by the electric force. So we are going to learn much more in detail about this concept when you go to the next topic. So to understand this concept, we'll go to this diagram. Now here I have considered an electric field. Okay. Now due to some charge configuration, let us consider there is an electric field that is created due to this plus Q charge. So here is plus Q charge, and there is an electric field that is created due to this plus Q charge, right? Now I am going to bring a test charge. Now where is the test charge? Now this is the test charge, small q. Small q is the test charge. Now this test charge is kept at R. Okay, so I have kept the test charge at position R. Now when I keep the test charge at R, now this plus q would have already created an electric field, yes or no? So when I keep a test charge in the electric field at position R, there will be a force of repulsion, yes or no? This is nothing but Coulomb force. We say that F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Here it will be capital Q into small q by R square, right? So there will be a force of repulsion between these two charges, right? Now what am I going to do? I am going to bring this test charge from the position R to the position P. Now what will be the direction of force of repulsion between these two charges? The force of repulsion will be outward, correct? Now I am going to bring the charge plus Q, which is a test charge, from R to P. Now what do I do here? I have to do some work, yes or no? So that work is done in the opposite direction to the direction of electric force. Electric force is from P to R, right? Or from P to R or from Q to R, right? But whatever work has been done, that is in a direction opposite to the electric force. So the arrow that is represented here is the work done by an external force. I bring an external force. External force is doing a work in bringing the body or in bringing the charge from R to P. Is it clear? So this work done, we are going to see now. I am going to discuss about this. Now, there are two things to be discussed here. First thing is when you assume a test charge. Now, here there is a test charge Q. Now, we have to assume that the test charge is so small. Why it should be taken so small base? Because if it is going to have a larger value, then it will create its own electric field and it will have its own electric potential. So to avoid that, we'll see to that the charge Q is so small that it should not disturb the electric field that is produced by plus Q. Clear? So this is first one. Now the second one is, now I am going to bring the charge Q from R to P. Now while bringing the charge, I should do an external force. I should bring an external force into play. This external force will does the work to make the body move from R to P. So we apply an external force just opposite to the repulsive electric force. Now this is the repulsive electric force. Fe is the repulsive electric force and F external is the external force which I am applying on a body to do the work to shift the body from, to shift the charge from R to P. Okay. So what is happening here? What will be the net force here? There is no net force and the charge will move with constant speed. So these two should be taken care. What is the first one you should take care? The first one is the charge should be so small that it should not disturb the electric field produced by plus Q, and the work done to move the charge from R to P or the external force must be just opposite to the Coulomb force. Clear? So what happens now? Now it is in this situation, what is happening? Work done by the external force is nothing but the negative of the work done by the electric force, and this is fully stored in the form of potential energy of the charge. So whenever this work is done in moving the charge against the electric force of repulsion, whatever work has been done, it is stored in the charge as potential energy. Okay. So I have shifted the charge from R to P. Clear? Now what I am going to do is, I am going to remove the external force. So if I remove the external force, what happens, children? If the external force is removed when it is reaching P, now what happens? The electric force will take the charge away from Q. Now again the electric force will come into play. It will take the charge away from plus Q. Now when it is moving away, whatever potential energy has been stored in the charge is converted into kinetic energy. Yes or no? So now it is converted into kinetic energy, and thus the sum of the potential and the kinetic energy is conserved. Is it clear? So this is about the work done. Now with this I am going to define what is potential difference. Now potential difference, before we go on to that, let me have the equation. Now what is this equation here? WRP. What is this WRP? Now it is the work done to move a charge from R to P. Now that is equal to F external dot dr. Work formula is force into distance, right? So force into distance. Now that is equal to minus, what is the equation here? It is minus Fe dot dr, which is the negative of the electric force. Is it clear, children? Hope you understood this equation. Now this is the work done by the external force. Now here this is the Coulomb force, which is due to the force of repulsion. So this work done is against the electric force, and this work done is stored as potential energy. So every point in an electric field Suppose there is, this is an electric field. Okay, so at every point in an electric field, a particle whose charge is Q possess a certain electrostatic potential energy. Every charge. Now I was talking about one charge. There are so many charges here. So every charge will possess some energy which is called as electrostatic potential energy. Now when you do a work, this work will increase its potential energy, which is equal to the potential difference between points P and R. So whatever work has been done, that will increase the potential difference, that will increase the potential energy between any 2 points, which is termed as electric potential difference. So what is electric potential difference? That the electric potential difference is defined as del U, which is equal to UP minus UR. Now U is the energy, potential energy. So potential energy at P, potential energy at R, the difference in their potential energy, which is nothing but you call it as electric potential difference. So whenever you define electric potential difference, you define electric potential difference between any 2 points. Is it clear, children? So, and one more thing you should remember here is, now here the work done or the displacement of the body from R to P, it should take place in the opposite direction of the electric force. So here the work done will be negative. See here I have a negative sign here. So it is considered to be negative. What is considered to be negative? The work done by the electric field is considered to be negative. Okay, so I am going to define now what is electric potential difference. Now electric potential difference between 2 points. So this is very, very important. When you learn a definition, you have to be very, very clear in this, children. Electric potential difference between 2 points. It is the work required by an external force or the work done by an external force in moving a charge from one point to another. So whenever you write any definition, it should be exactly correct. You cannot do any mistake while you write a definition. Okay. So I repeat once again, electric potential difference between 2 points is the work required to done by an external force in moving a body or moving a charge from one point to another. Now the unit of potential difference is volt. Okay, or I can also write the formula for potential difference to be, actually it is represented by V. So it is Vp minus Vr is the work done by a test charge, or the unit for this also can be written as work done is measured in joule and charge is measured in coulomb. So joule per coulomb is also the unit, or it is also volt. Okay. So this is about potential difference between 2 points. Now when you say the potential difference is to be 1 volt, when the potential difference is 1 volt, when you do 1 joule of work. Now this is there will be a question as how to define the unit of potential difference. As I said you, the unit of potential difference is volt. When the potential difference is said to be 1 volt, the potential difference is said to be 1 volt when 1 joule of work is done to move 1 coulomb of charge from one point to another. Okay, so very important definition. Now, what are the 2 points that you get from this? The first point is, whenever we talk about the work, okay, the work done by a body, or here the work done by a charge, the work done by an electrostatic field In moving a charge between 2 points, it does not depend on the path. That is, it does not depends on the path, which means it is independent of the path. It depends only on the initial and final position. Okay, it is not dependent on the path through which it is traveling, but it depends only on the initial position of the charge and the final position of the charge. Okay, so this is the basic concept of conservative force. That is why we say Coulomb's law comes under conservative force. Okay, now whenever we talk about electric potential difference, now electric potential difference is discussed in terms of work. Okay, so whenever we talk about simply potential energy, it is not significant, but it is only the potential energy difference that is making it significant. So when I add a constant to this term, now here what I have done is up minus ur, I have added a constant here, so that the difference in potential difference will not have, the difference in potential between any 2 points will not be changing. So when you add a constant to potential energy at every point, now the value of potential energy difference will not change. Okay, now I am going to define you what is electrostatic potential. Now we were so far discussing about what is potential difference and potential difference between 2 points. Now I am going to coming to the main topic, which is called as electrostatic potential, which talks about now the definition of electrostatic potential comes from potential difference between 2 points. Now in potential difference between 2 points, we consider 2 points. One is R, the other one is P. I will move the I will move the charge from R to P. Now here, to define electrostatic potential, I am going to consider the point R to be at infinity. So when you consider the point to be at infinity, so when I substitute instead of R, I am going to substitute up minus u infinity. So when it is at infinity, the work done will be, now here this term will become 0. Potential at infinity is infinity in the sense when the charge is at a very far distance. At a very far distance, the potential is considered to be 0. So what is potential energy at infinity? This becomes 0. So what will be the value of work done? Work done will be simply up. So when you consider potential energy of a test charge in terms of work done, this is work, or this work is proportional to Q. Is it clear? So work done per unit charge is nothing but the characteristic of the electric field associated with the charge configuration. So I can write this: work done by an external force in bringing a unit positive charge from R to P is Vp minus Vr, that is equal to, this is what I wrote in first, that is work done per unit charge, Up minus Ur by Q. So what is electrostatic potential at that point? What is electrostatic potential? I am going to bring a charge which is at infinity to a particular point. See here, work done by an external force in bringing a unit positive charge from infinity to the point is nothing but, you call it as electrostatic potential. Now we derive the expression for electrostatic potential from potential difference. In potential difference, we consider the 2 points to be in the electric field. But whereas here I am taking the point R at a finite distance, at an infinite distance, then the value of R to be 0, because potential at infinity will be 0. Now I define what is called as electrostatic potential. So when I define electrostatic potential, it is nothing but is the work done in bringing a unit positive charge. I'm going to bring a unit positive charge from infinity to that point. I'm bringing R is at infinity. I'm bringing the charge Q from R to P, which is at infinity, to a particular point. You call it as electrostatic potential. And here also the unit of electrostatic potential is V once again, and it is also said to be a scalar. Now, when you can say the electrostatic potential is said to be 1 volt. Now, the electrostatic potential is said to be 1 volt. When 1 joule of work is done, you do 1 volt, you do 1 joule of work to move 1 coulomb of charge from infinity to a particular point. Okay. Now, if you want to find out the work done per unit test charge, you have to take an infinitesimal test charge. You have to take for a small work done, and what is the work done in bringing a unit charge from infinity to a point, and you can determine the electrostatic potential. Okay. So, this is about the introduction of electrostatic potential, where you learnt about very important two definitions. One is electrostatic potential difference. The other one is electrostatic potential. And you have to once again recall what are conservative paths, because as far as these two topics are concerned, the path or the work done, it is very important, and you have to very clearly know about conservative forces. So definitely go through this topic. Tomorrow we'll be continuing with potential due to a point charge. Okay ma, so please go through the pages and start learning. Okay, see you children.